But there will also be we'll be sending out like a schedule of the symposium. It's a full day event. It'll start at 8 and at 5 we'll have a breakfast and a lunch. And there'll be a bunch of different like speaker slots you can go to. You don't have to go to all of them, but we highly encourage you. So yeah, that's that, and I'll hand it off.
Thank you, Aaron. So yeah, if you're interested in data science, consider joining. But the cool thing about cybersecurity is that it kind of overlaps with any field. So there's actually a lot of topics where data science and security work together. Basically, if you're a math node, data science might interest you. Today, we're going to be talking about cryptography, which is pretty math heavy. If you don't like math, that's okay. I'll try to make it interesting and understandable. But if you like math, yay, that's really cool. You should probably do more cryptography, especially more CTFs. We have a CTF team that meets every Thursday. So you should come there. It's kind of fun. In fact, we have our own in-house CTF this weekend. So if you're interested in that, consider attending. Um, Also, data science, everyone probably knows AI, machine learning, those things are big. Cool aspect of cybersecurity is that we can actually hack AI to give it malicious prompts. And so Adam's going to be giving a talk on that next week. And so it would be cool if people start looking into that because next year we could actually compete in some AI specific competitions, which have big payouts. So Grace One, if you're interested, that's pretty cool to look at. Another thing is Cram is this really big competition with big payouts. Last year, it was very like threat hunting, threat modeling using data science, AI, and machine learning to kind of um, do math modeling of threat actors and stuff like that. We're not sure what the theme is going to be next year. Might be similar, might not. I don't know. We'll check it out next year. But with that, let's start talking about cryptography. So cryptography has a long history. Um, and there's a lot to it. If you want to practice, crypto hack is a great way to start learning and delving into actually doing cryptography. And as for tools, CyberChef is a really cool tool that kind of gives you all the different types of cryptography in one place. So you can just put in your input, throw some stuff together, and it gives you your output. So that's pretty neat. But let's talk about actual cryptography. In the old timey days, cryptography was really simple. It wasn't really about encrypting your message. It was more just making it confusing so people don't want to read it. So this isn't really used nowadays because it's not super secure, but it's super fun to look at. So let's talk about it a bit. The first major one is the Caesar cipher. Literally, all it is you take your alphabet and you shift it, you rotate it. So instead of A, for example, you could replace it with B. Instead of B, you replace it with C. We just shifted our entire alphabet by one letter. And you can shift it by however much you want. For example, right there, I have Caesar cipher shifted by 13 digits. And you get that message there. So this is actually a specific example of the Caesar cipher called ROT13. And the cool thing about ROT13 is since there are 26 letters in the alphabet, if you apply it twice, you get the original message. So it's something we call an involution in math. If you don't just want letters, if you also want numbers and other symbols, there's ROT47 for that. So if you're doing baby intro crypto and you see words like ROT13, ROT47, it's a very easy challenge. You just throw it in and you get the result. Another thing that shows up a lot is base 64. Basically, each byte of data is made up of 8 bits, right? So that's going to be base 256. Base 64, all it does is it takes that data and splits it into chunks of 6, because 6 bits make base 64. So you can actually see there, I have my data. We have 3 bytes of data, which would mean 24 bits. We can split them into chunks of 6. And so then each chunk would be a number or like a character in base 64. And so you can see up there is the message base 64 encrypted in base 64. So that's something you see a lot. How you identify it is if it looks like alphanumeric characters just strung together, or if you don't have enough bytes, because we say every 3 bytes makes 4 base 64. What if you don't have enough? then we're going to start padding it with these equal signs. So if you see a weird long message with equal signs at the end, that means it's base 64. So you just unbase 64 it and wow, you got your message. So that actually shows up a lot in places like malware and stuff like that. Another thing that shows up a lot, especially in malware is XOR. So XOR is this function in math. What it does is, let's say we have 2 bits, right? Our message and our key. And when we XOR the 2 bits together, it's basically going to compare all their values the same or different. And you can see in that table there, we have the zeros, the ones, or the zeros. So oftentimes when we have a key and we want to encrypt data, we can XOR our data with that key to get encrypted data. This is a very simple way to XOR, very easy to do, really annoying to crack. There's this whole set of challenges just about can you XOR the data and figure it out. I'll post them later once I finagle it a bit. But XOR, pretty fun, pretty simple to get started with, but can get really, really difficult. And so actually right there, I have an example of, right here, we have a base 64 thing. You have our original message up here. And then I XORed with the key, I think that's L, and then just 1 and L. And you can see with each bit, it changes. So since these are the same, it's zeros. Since these are different, it's ones. Do those 3 encryption mechanisms make sense to y'all? Okay, cool. So this is the old-timey stuff. It still shows up in CTFs. These ones are the most relevant. There's a bunch of other ones that I think are super fun and interesting. Morse code, that's awesome. I love Morse code. Braille, and then all these other ciphers. I can go on and spend the whole day talking about them, but I'm not because they're not useful anymore because they don't actually encrypt your data. So let's talk about something that's actually useful, which is modern day encryption. This, instead of using fun tricks and puzzles, uses math. Math makes things secure. And so if you like math, you'll like this. So in our setup, we have 2 people that want to communicate, Alice and Bob. They want to send a message to each other. However, we don't want anyone else to listen to what they're sending. They want to keep their communication secret so that no eavesdropping Eves can pick up on what they're sending. So how are we going to securely transmit this information? Well, the solution is with something called a trapdoor function. Think of a lock, right? When it's unlocked, it's very easy to lock again. You just push it down and now it's locked. But to unlock it, you can't just pull it out. It's very, very difficult. You can lockpick it if you want, but that's annoying and that takes a lot of time. But if you have the key specifically made for that lock, it's very easy to open. So this is the idea of a trapdoor function. It's very easy to go one way, very difficult to go the other way, unless you have your key. So what we want to do is we would want to find a math function that acts as a trapdoor function. Very easy to go one way, very hard to go another. And in cryptography, the message we want to send is called our plain text, and the encrypted message is called the ciphertext. So far, everyone follows? Okay. So let's go ahead and explore what could that function be. So first, actually, I want to talk about there's 2 different types of cryptography. You could have symmetric encryption or asymmetric encryption. So the idea is when we encrypt our data, we're going to use a special value called our key. And when we decrypt it, we use a key to help us decrypt it. So in symmetric encryption, the idea is we use the same key for both operations, both to encrypt and both to decrypt. Because of that, we need to keep that key secure. Because if we just post it on the internet, now anyone has our key. Anyone can decrypt our message. And that kind of defeats the whole point of cryptography, right? So in symmetric encryption, we have a single private key that we use to encrypt and decrypt our data. This is really fast because usually our key is small, so we don't have to do a lot of computation. However, it's very difficult to keep that key secure, especially if I'm Alice and I want to send a message to Bob. How am I supposed to get my key to Bob in the first place? So that's the thing about symmetric encryption. Really quick, but difficult to distribute keys. Asymmetric encryption, on the other hand, utilizes the idea of a trapdoor function where we give out a public key and we say, hey, anyone, here's my public key. This is what you're going to use to encrypt. Okay? So Alice would give Bob her public key, or rather, she would post it on the internet. Bob encrypts the message and sends it to Alice. Now, Alice is the only one with a private key. She holds on to it so no one else can use it. And that allows only her to decrypt the message. So asymmetric is different from symmetric because symmetric had one private key. Asymmetric has a private and a public key. These keys are usually really, really big, which makes this computation really, really slow. However, it's a lot more secure because we're not giving away our private key. So this is the idea of symmetric versus asymmetric encryption. Any questions so far? Okay, cool. So this is just the theory behind it. Let's go ahead and talk about how do we actually carry this out. So for a moment, let's talk about math. Who here likes math? Yeah, we love math. Okay, okay. So I'm sure in like kindergarten, you guys, you were doing that multiplication and you're like, oh, this is so easy. I can multiply all the numbers I want. It's it's not that difficult. There's a very simple procedure to follow. 5 times 3 is 15. We know how to do the carryover and stuff like that. So multiplication we can do, but division, it's not so easy. If I just say a number like 231, what does it divide into? Is it simple? 6? Yeah, it's 21 and 11, so 3, 7, and 11. That isn't that simple as asking, hey, what's 7 times 11? Right? Multiplication is really easy because there's only one way to do it. It's sort of deterministic. Division is very hard because there's so many possibilities. Just from a single number, we can't figure out what it is unless we iterate through all possibilities. So that sort of gives us a trapdoor function. Multiplying, super easy to do. Dividing is really hard. But it's not so hard if I give you one of the factors. For example, if I said, here's a number, 91, and then I give you the number 13, you know how to divide 91 by 13. And so you could realize, oh, 91 is 13 times 7. When you're given one piece of information, it's a lot easier. So that would be our private key in this scenario that helps us decrypt our message. But that's too easy for computers. Computers can just multiply. It can iterate through all the numbers and figure out how to divide a number in O of log n, which in computer science terms is pretty quick. So let's make it more complicated by introducing the idea of modulo. Who here knows how modulo arithmetic works? Okay, some people, a decent chunk. So I'll go over it a bit so we can all understand. Modulo basically says instead of having all the numbers, let's restrict it to a finite set. So here at the bottom, I have modulo 15. And we can see that all the numbers, it goes 1, 2, 3, 14, and then 0 instead of 15. Why? Because 15 is divisible by 15. We can write it as 15 plus 0. 16, we can write as 15 plus 1. So the idea of modulo is when we have a base, in this example 15, we're going to represent any number as just the residue when we divide by our base. Make sense? Okay, cool. So the cool thing about modulo is it is incredibly difficult to divide in modulo arithmetic. So like if, for example, like in the base 15, what's the inverse of 3? In other words, division is sort of like inverse multiplication. So I'm asking, what number do we need to multiply 3 by to get 1? Or rather, let's do 4. What number do I need to multiply 4 by to get 1? Division already was pretty hard. Division in modulo is even harder because we're losing information. We don't have the full number, we just have that residue. So modulo math is difficult, and that's how we're going to do cryptography. A lot of cryptography is based and mods. So let's go over this example here. This is the basis of RSA encryption. RSA, what we do is we take two really big primes and we multiply together. And that's how we're going to do our encryption. So in this case, our two numbers are P equals 5, Q equals 3. When we multiply them together, we get 15. And then here I have this symbol called Euler's phi function. Basically what it is it's asking how many numbers less than this number are relatively prime to it. For example, in this case for 15, we see that 1, 2, 4, 7, 8, 11, 13, and 14 are all relatively prime to 15 because none of them are a multiple of 3 and none of them are a multiple of 5. And so there we have this quick calculation where if you know the components, it's very easy to find the Euler's phi function. So the reason this function is cool, and we could prove this mathematically, but I'll save you guys the BS, is when we raise any number by this power, it's going to be equal to 1. Or rather, it's going to be equal to 1. So what this allows us to do is, let's say we have some data, right? And we raise it to some ugly power, so it mixes up our data. If we ever want to go back to the original, if we ever want to go back to 1, we just need to make it so that it's raised to a power of phi. So for example, we have the numbers P and Q. If I pick two random numbers, for example, let's say my number is 4. I tell you guys 4. 4 is your number. Whenever you want to encrypt something to me, raise it to the power of 4 and send that to me. That's pretty easy to do. You guys know how to exponentiate things. But only I'm going to be able to decrypt it because only I know that these two numbers multiply to phi. So when you give me your number, when you give me a to the d, all I need to do is raise it to the power of e. Because then I get a to the e times d, which is just e to the phi, or the Euler's phi function, which is 1. So when you give me your encrypted data, I just have to raise it to the power of my private key to get the original message. Does that make sense? Any questions? So this is the idea of RSA. And when we actually do RSA, we're not going to be doing, sorry, there was a typo. We're not actually going to be doing 3 and 5. That's super easy to crack. Instead, we're going to be using like 5, 7, 10-digit prime numbers and multiply them together. So you end up getting these outrageously huge numbers. That's basically all there is to RSA encryption. And like here, I have a little doodle of if we have the number 2, let's say we want to encrypt, can raise it. Oh, never mind. Ignore that. Any questions so far? No? Okay. So this would be an example of asymmetric encryption because we have two different keys. The private key that we keep to ourselves and the public key that we give away. On the other hand, we have an example of symmetric encryption, the most popular one being AES. Okay, so how AES works is really confusing. Honestly, the reason AES is secure is because we do so much to it that even computers can't figure out how to decrypt it. So like here first, we basically represent our data, 16 bytes, into a 4x4 matrix. Then we say for each byte, let me look up in a table and replace each byte with a different byte, depending on what its value is. So this is just like a function that transforms from one to the other. And then after that, let's say we mix all the columns. So we're now going to rearrange our columns around. And then after that, we're going to shift the rows. So they're not on the same rows. You can see now it's like slanted like that. And then after that, then we XOR it with our original key to get the final step. But we're not done here. Now we're going to repeat this whole process 10, 1,000, however many times you want. That is how AES encryption works. And it is difficult to crack, like very difficult. In fact, it is so hard that computers have custom built-in implementations just to handle AES. So your hardware actually would have a specific function built into it to handle AES encryption. Usually it's called AES-NI. If your hardware doesn't come with that, instead we use something called T-table lookups, which is basically a magic table that says if you're given this input, this is your output. And that's how they do the encryption. But T-table lookups are vulnerable to things like side channel attacks, which I covered last semester. So yeah, that's how AES works. Any questions there? Okay. I'm not going to talk about why it's secure because it's already confusing to understand how it works. Just know that AES does a bunch of stuff and it works. And the reason it's symmetric is because if we want to decrypt it, we just run it through the same process. Here we use an XOR on our key, right? And XOR is going to be a symmetric process. If I have a number and I XOR it, and then I XOR it again by that, I just get the same number in the end. So yeah, AES is an example of symmetric encryption, and RSA was an example of asymmetric encryption. So now, where are we? Alice and Bob now know how to communicate securely. We just need to have our private key, and then we can use either AES or RSA to transmit a message between the two of us. But then that begs the question, how do you distribute that private key without anyone else knowing? One thing to do would be to physically meet up with the person and say, hello, here's your key, keep it safe. But that is kind of difficult to do when you want to communicate with, let's say, everyone on the internet, right? That's kind of hard. So we need to figure out how can we transfer keys securely on the open internet so only my target recipient has the key. So this is kind of strange. We want to send information out for anyone to see, but make it so only one select person has that private information. So how are we going to do that? Diffie-Hellman is how we're going to do that. So how Diffie-Hellman works is it relies on that idea of let's raise numbers to a power. So basically, Alice and Bob are going to say, hey, Bob, let's agree. We're going to use prime number, this prime number, like 13, and we're going to use a generator, like 2. What is a generator? So a generator is, let's say in this example, we have the number 7. 3 is a generator of 7. So let's just do a bit of quick math. 3, what's 3 times 3? 9, which is what, mod 7? 2. And then what's 2 times 3? 6. What's 6 times 3? 18, which is 4 mod 7. What's 4 times 3? 12, which is 5 mod 7. What's 3 times 5? 15, which is 1 mod 7. You see how when we use this number and we just keep raising itself, like multiplying it by itself over and over again, we iterate through all the different residues that modulo. So that's the idea of a generator. So basically, what we're going to do is we're going to start off by agreeing on a prime number and on our generator. And the reason we do that is because then we can raise that generator to a random power. Oops. So after the first step, after we agree on that prime number, then we're going to say Alice is going to send her number to Bob. Alice picks a private key, A, and she's going to raise the agreed upon generator to that power. And so she's going to send Bob G to the power of A. Then Bob has his own private number B, and he raises his generator to the power of B and sends it to Alice. Does this make sense so far? Basically, yes, Lucas. Publicly, I just say, hey, Lucas, what prime number do you want? 5. Okay, guys, that's our prime number, 5. Hey, Lucas, what generator do you want? It has to be a number smaller than 5. 3. Okay, 5 and 3, that's our numbers, guys. That's it. On the open internet, anyone can hear this. This part is all open for anyone. Then I'm going to make a number for myself and keep it private to me. And then I'm going to tell Lucas, hey, Lucas, my number is 4, okay? That's my number. G to the A, that's 4, okay? Hey Lucas, what's your number? Can you tell me? Three. Okay, his number. Okay, is B one. Okay. So, anyways, that's what occurs. All of this occurs openly for anyone to hear. So the question then becomes, how do we get something private from this? How is this secure? Well, the trick is Lucas on his own is going to take the number I gave him and raise it to his private power B. So I gave him G to the A. He has B on his own. So now he has G to the A times B. And that's going to be his private key. Meanwhile, he gave me G to the B, and I have A to myself. So I can take G to the B, raise it to the A, and now I have G to the A times B. So let's stop for a moment. I right now have G to the A times B. Lucas right now has G to the A times B. We both have G to the A times B. That's our private key. Now, what makes it private? Why isn't this public? Didn't we disclose all of this information openly? Sure, we told some information, like G to the A and G to the B, but not everything, right? Because A and B themselves are kept to us. If you're a random stranger like Adam listening to our conversation, how is he going to figure out how to get G to the A times B when he only has G to the A and G to the B? You could try multiplying them together, but then you get G to the A plus B, not A times B. So that's how this works. This is how we can create a private key together on the open internet. Any questions about that? Is this talk boring you guys, or is it interesting? Okay, cool stuff. Okay. I thought this was really cool because I'm like, how's that even possible? Like, all of this is public, but somehow we get private stuff out of it? That's fascinating. So, did we solve the problem yet? Can we communicate completely securely? The answer is nope. Because now, instead of before, we had Eve, our malicious actor, was just listening to all of our traffic. They were listening to all the stuff we were saying. What if instead of just passively listening, they became an active threat and were a man in the middle? Essentially, whenever Bob or Lucas tries to send a message to me, Eve, or in this case, Leo, is going to intercept that message, keep it to himself, and send me a new message pretending to be Bob. So Eve intercepts all of Bob's traffic and forwards traffic to me pretending to be Bob. I send traffic to Bob, but Leo intercepts it and sends message to Bob pretending to be Alice. Okay? So basically, Alice and Eve form a secure communication between them. Eve and Bob form a secure communication between them. Alice never directly communicates to Bob. Alice thinks she's communicating to Bob because Eve says, "Hi, Alice, I'm Bob." And then Eve turns around and says, "Hi, Bob, I'm Alice." So this is the idea of a man in the middle. For our Diffie-Hellman key exchange, we were only able to establish secure connection between two people. So now these two have a secure connection and these two have a secure connection. But Eve is able to see all traffic between Alice and Bob because Eve can decrypt Alice's traffic and Eve can decrypt Bob's traffic. So this is a problem. We don't have secure communication. How are we going to fix it? And the answer is, this is too hard. I'm going to let someone else handle it for me. We have a third party called a certificate authority that basically everyone trusts is secure. And we send messages to them to sign our requests and say, "Hey, third party, can you verify that I am legitimate?" And then they'll be like, "Yeah." And now you've verified all of your communications are legitimate. If Eve tries to intercept the traffic, the certificate authority is not going to sign their messages. So Eve won't appear as legitimate because they haven't been verified by the third party. And so that's kind of a cop out, in my opinion, but that's what we do. So any questions or suggestions on any of that? Yes, Ishan.
Alice, yeah. So this technique that he mentioned, I think it's called like the digital signature technique. You also have another technique where Alice will sort of like use the text she's sending to sort of create a tag that goes along with her ciphertext. And that's called the authentication tag. So Eve, even though Eve intercepts the authentication tag, the only way Eve can change the message is by changing the associated tag. But the tag is computed in such a way that Eve cannot just change the tag on a whim. So that's called like authentication system. That's what's used by really that's what's used in like really sensitive data, like your credit card information. Every time you use Apple Pay, they use authentication using tags. So yeah. Mhm. So, yeah, so ideally, the tag is computed using the ciphertext. So if Eve wants to recompute the tag, then Eve would ideally want another ciphertext to go along with the tag. But the issue is recomputing the tag using a different ciphertext is relatively what's considered to be hard. So for like these authentication systems, what they do is that each ciphertext that you send across to like any other person, when viewed by like a intermediate party, is literally the same as just seeing random bits go through. It's very hard to establish patterns unless you make like a huge load of queries. That'll take you years to establish. So there's no way they can basically compute a valid tag using another ciphertext, uh, unless they have access to like a really like fast supercomputer. Yeah, ideally. But that's pretty hard to establish in practice, which is why you only have like these banks and like super like people with like tons of compute resources who can actually do like this authentication system. Otherwise, you obviously use like the thing that you mentioned. Mhm.
Thank you for sharing that. Okay. Yeah. What's your question? Yeah. Go ahead, ask your question. Log base G. Log base G. Oh, yes. So that's a valid point. If we were using regular numbers, that is completely true. But everything we're doing is modulo our prime. So ideally, you could just take log. But the problem is when we do things in prime numbers, we don't know what the actual number is. We just know that residue, right? So if I sent you 3 to the 7th power, that's going to be a huge number, right? Can that fit in base 7? No, it's going to be one of these random residues. And just given a residue, it's very hard to reverse. In the same way that just given a residue, it's very hard to divide, the same is true for exponentiation. Because raising to an exponent is basically just repeated multiplication. So if division is difficult, repeated division is also going to be difficult. Does that answer your question? Okay, cool. Any other questions? No? Okay. So that is like basically the current standard of cryptography. However, what's the future of crypto? One thing is blockchain crypto. You can make a lot of money doing this. I don't know how to, so we're not talking about that. The thing I'm going to be talking about is different types of computing, because all of this cryptography, what it relies on is certain problems are difficult to do. Our trapdoor function is difficult to compute. So what if we just made a better computer so that we can do all those calculations? That's the problem that we reach as we head into the future. For example, quantum computing supposedly can allow for vastly greater calculation speeds, right? And so if that is the case, if we can compute things much quicker, then we will no longer be able to keep our messages secure because we can just throw it into a quantum computer and it will be able to crack the code. So just a quick, very quick brief on quantum computing. Bits can be 0 or 1. In a quantum computer, we use qubits, which can be 0, 1, or any combination in between. Now, this may seem absurd to you, and it is, but this is how reality works on the atomic level. The thing is, these atoms exist in this myriad of possibilities, but when you actually measure it, you can only measure 0 or 1. So the whole idea of quantum computing is let's manipulate these qubits in such a way so that we utilize this full myriad of possibilities. But in the end, when we measure, we know that it's going to be exactly 0 or exactly 1. And just from that, we can tell all the mumbo jumbo that happened in between. So because of this, there's very strict requirements. We need our end state to be specifically 0 or 1. And as a result, only very specific algorithms can work. And the two most popular ones are Shor's algorithm and Grover's algorithm. Quantum computing is not a solution to solve all your problems. It is very application specific. And here are two very specific applications, which happen to be cryptography based. So RSA, if quantum computing works, which we'll see about that, would be bad. AES still works, actually. We would just have to double the number of bits. So right now, if we use AES 256, we would just need to use AES 512, double the number of bits, and then our communication is still secure. Because quantum computing is good, but it's not that good. And so basically, because quantum computing, they break everything, people are coming up with new complicated encryption signatures. If you're interested, look into them, but I'm going to move on for the sake of time. The other thing that is fascinating about the future is we can now use DNAs as computers. So the thing about DNA is, right, we have bits. They exist as 0 or 1. But guess what? DNA has bases, not bits. So instead of 0 and 1, we got 4 possibilities. That's a lot more than 2 possibilities. And as a result, this gives us more information within a single unit. As a bonus, nature has spent millennia evolving DNA to be super duper compact. So essentially, DNA provides a natural solution to very compact storage of data. So DNA computing is this new emergent field where we basically create a computer in a vial of DNA. It's just like this big and it can do computations. It's not very good, but it can happen. The really cool thing is it has immense storage capabilities. So as you can see there, instead of having a huge warehouse full of RAM and forms of storage, we can just have a tiny vial of DNA, and that has all of the data we need. So the cool application of this into cryptography is we're no longer restricted by the size of our keys. Before, it was a memory-based issue. If we have big, big keys, it's going to be hard to store them all. But if we have super compact storage, we can make our keys really, really big. So those are just two quick things I wanted to mention. Any questions about that? Okay. So if not, that's the end of the theory talk. Now we'll talk about actual applications. So go ahead, Ishan.
Hey, so what's up, guys? I'm Ishan from DSI, and I'll help you guys take a look at like typical cryptography problems that you'll face in CTFs, or just in general problems that you can like crypto-ish problems that you'll see maybe in like coding interviews for companies, cybersecurity companies. So if you look at the screen, like a typical cryptography problem has you being given access to some oracle. So you have to think of cryptography as like some way to essentially find out behaviors of like some hidden function. So you put in the input through a hidden function, you get some output, and based off that input-output pair, you essentially want to learn stuff about the function it's going through. So this function is called like a black box. In the case of cryptography, you have plain text that goes into the black box. You have a key that defines the black box. So if you change the key, the way the function or the black box behaves changes, and then you get a ciphertext out. So essentially, in like most cryptography problems, you'll have this sort of weird oracle relation between inputs and outputs. And you might want to find out information about the key, or you want to find out different inputs that map to the same output. That's what's called a collision. And I don't know how many of you guys know what SHA-256 is. Yeah, everyone knows it, right? So everyone also knows that the earlier versions of it were broken once like collisions were found. So that's a potential like cryptography problem. So I have like a small cryptography problem that we can like talk about. I don't know if like someone will be able to solve it within like 15 minutes that we have, but the gist of the problem is you have an oracle, and again, think of oracle as like a black box that takes an input and returns an output. In this case, we take an input that goes from either 0 to 2 raised to 30. So it's essentially, it takes in 30 bits as its input. The oracle is defined by a key x comma y, which is unknown to you. And x and y each are again 30-bit keys. So each time you feed the oracle an input n, it returns n bitwise or x plus n bitwise or y. And the sort of like standing like line symbol indicates a bitwise OR. So as like Andre mentioned, it just goes through each bit of your n and x and ORs them together. And so n or x will go through each bit of n and each bit of x, OR them together and return n or x. And then you add that to n or y. And so that's basically the output that you get from this oracle. So you are allowed to make two queries to this oracle, which means that you can feed it two different inputs and you can look at the outputs that it returns. And then you are asked a query M. That means I'll basically allow you to make two queries to the oracle. You see the input output pairs. And then I ask you a question, I ask you a query M, and you have to tell me what M or X plus M or Y is for an arbitrary M query. So does everyone sort of understand the question? It's like you're given two input output pairs, and then I give you an input of my own, and you have to tell me what the output for that will be. So does anyone have any intuition for how you'd go about this problem? Or does anyone have like a query that they think is like useful in this problem? Any like any simple query can work. So I guess like I can like start off with like one simple query. Does anyone know what will happen if I query the bit string that's made up of all zeros? So if I put in an input of like 0, does anyone know what the output that I'll get will be? Yeah. X plus Y. Yeah, exactly. And so if I put in the input that's the bit string of all ones, does anyone know what's the output that I'll get? Yeah. Yeah, exactly. So you can see that some queries, that's essentially the bit string of all zeros, gives us way more information than the bit string of all ones. So that's how we can basically see that some queries work better than others. So maybe like let's take a look at the solution. So the first thing to basically notice is that every time you work with like cryptography problems, you want to express numbers as that bit representation. So the next step is essentially to break the problem down into simpler, like into a simpler problem. So instead of working with like 30-bit numbers, let's just work with like 4-bit numbers. That is that we'll restrict n, x, and y to be from 0 to 2 raised to 4. And this will allow us to basically like select an x and y of our own and basically figure out how we'll make two queries that will allow us to like recover x and y. So you can see that numbers will be expressed as 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, and etc. So when you really think about this problem, you don't really need to know what x and y are. Like the question isn't asking you to asking you whether like to recover x and y. It's asking you to like basically tell the output for like a random query that we'll ask. So it's enough for us to know what m or x plus m or y is. So that basically tells us that we need to know at what positions do x and y have 1 bits. Because if x and y have 0 bits, then essentially ORing them with like m will have like no effect. The only time it will have effect is when a position of like x or y has a 1 bit. So you can see that this is like an example that I've given with like, I pick like x and y of my own, and then I pick like a query that's like 1, 1, 0, 0. And then I compute n or x and n or y. And we can see that n or x is only affected by x when n has a 0 bit and x has a 1 bit. If n has a 1 bit and like some index, then ORing it with anything won't matter because what you'll get back is 1. When n has a 0 bit and you OR it with like a 0 bit again, then you'll just get back the bit that was there in the original place. And when you OR it with like 1, that's when something actually changes. That's when n or x will actually change from what it was earlier. So you can also notice that the oracle basically gives us n or x plus n or y, but n or x will always be greater than n because you're basically changing 0 bits to 1 bits, but you're never changing 1 bits to 0 bits. So that means you'll always increase the number of ones in the bit representation, which will mean that the number that you get after ORing will always be greater than the number you originally had. So we can see that once we subtract 2n from like the output that we get, we'll essentially understand what is the amount that was increased from like the function output. Essentially, how many number of ones were actually like flipped once we like made the query to the oracle. Because in our original 2n, there are no bits that are flipped, but once we put it through the oracle, x and y flip some bits and then return us the output. So, for example, if n and x and n or x and n or y flipped 0 bits, then n or x plus n or y minus 2n would be 0, because nothing would change between the output and what it's supposed to be. So the higher the difference between n or x plus n or y minus 2n, the more bits it flipped. So in this particular case that I've given here, you can see that um, only one bit is flipped by y. N or x returns the same thing that n is, and n or y returns a string that has one bit flipped from like what n was. And so you can see that the bit that was flipped was at the third index, so at the second index, which means that it added 2 squared to the sum, which means it added 4. So now that we sort of know this, we can look at queries like the one I've like shown there, which is 0101 and 1010. So essentially the bits of 1 being at all even indices and bits of 1 being at all odd indices. So we do the same exercise again. We find out what n or x is, n or y is, and we subtract 2n from it. And we can see that we get 10 as like the difference. So essentially the number of bits that were flipped, gave us an increase of like 10 from our original input. So you see that our query looked like 0101, which means that only the bits at like the even indices could be flipped. Now the max amount of increase that you can get from the OR operation is essentially flipping all 0 bits that were there in our n. So you can see if I flip like the bit at indice 3, I'll get an increase of 8, because 2 raised to 3 is 8. And I can do this for like the 2 n's that I have in the output. That is, if I can flip the third bit for n or x and n or y, and I can flip the I can flip the fourth bit for n or x and n or y, and I can flip the second bit for n or x or n or y. So the maximum increase that I can get is something like 8 plus 8 plus 2 plus 2, that is 20. But we know that the difference that we got is like 10. So seeing that you can see the how we can construct differences. We see that 1, 8 and 1, 2 gives us 10, which would ideally mean that the x and y that we used to like OR it together flipped 1 bit in the fourth position and 1 bit in the second position. Because if we flip those bits, then you can see that we get an increase of like 8 plus 2, which is 10. So that signals to us that 1 of x and y have a bit equal to 1 at index 3, because that's what caused the flip at index 3. And 1 of x or y have a bit of 1 at index 1, because that's what flipped it. We know that both of them don't have a bit of like 1 at like index 1 and 3, because if both of them had a bit of 1 at index 3, then we would have an increase of 16. But we know we don't have that. And if both of them had a bit of 1 at index 1, then we would have an increase of like 4. But we know we only have an increase of 2. So we can see that this basically allows us to figure out at what indices of x and y we have like 1 bits. And then we do the same thing with the other query, which is essentially have a query that has 1 bits in all of the even positions, which will allow us to figure out what x and y have as like a 1 bit in their odd indices. So you can see when we query like this 1010, we get back an output that's 25. And when we subtract that from what we're supposed to get, which is 2n, we get an output of 5. So doing the same exercise here, you can see that the max increase is 4 plus 4 plus 1 plus 1, which means that 1 bit was flipped in the second indice and the 0th indice. So we know that x or y have 1 bit as like 1 in the second and the 0th indice. So putting this all together, we finally understand that at least 1 of x and y have a bit equal to 1 at index 2, 1 of x and y have a bit equal to 1 at index 3, and so on up until 0. So we can now make an assumption that these bits are 1 for like, let's say the choice of x. So let's assume that it's only x that has all of these 1 bits. Then that would imply that x is equal to all 1s and y is equal to all 0s. Because we can only have 1 bit at like all of these indices from our calculations. But notice that these like keys that we've recovered for like x and y aren't the same as the ones that we originally picked. We originally picked, I think it was like 1001 and 0110. So you can see that these aren't the same things. But we don't care, because we just want the output of like our query that we are given to be the same. We don't want to like recover the key specifically. That's something important that you have to keep in mind in cryptography problems, is that you want some way to sort of hack the solution and not necessarily do it in the hardest way possible, which would be to recover these keys. So now let's put like an arbitrary query M, which is 0100. And you can see that once I OR it with X and Y, I get like an output of 19. And once I put this query M through like our original keys that we had, which is X and Y, I get the output back, which is 19, which means that I basically found a way to figure out what positions of X and Y have one bits in them. And through that, I could basically like figure out how to basically construct an output of this black box. So we sort of solved the problem, and you can see that arranging the number of like ones that we had, like we saw that one was at index 3 for like X or Y. So if we pick X to be like the X to be the key where we have a 1 bit at index 3, Y to be the key where we have 1 bits at index 2 and 1, and X to be the key where we have 1 bits at index 0, we can recover the same key again. So this is sort of like the way in which you solve cryptography problems. I guess that I know that I had to like rush through it because like we have less time, but I hope that this was sort of instructive as to how to go about these problems. Thank you. Yeah, sorry, go on. Yeah. Hmm. Yeah, so exactly, yeah. Because you can see that if I query all 0 bits and all 1 bits, the 0 bits to the left side will interfere with each other. Because if I OR two consecutive 1 bits next to each other, they'll basically shift the answer by like 1 bit, and it becomes difficult. So you want to segment them in such a way that ORing them won't like affect the output of like the thing that you get essentially. Okay.
Okay, thank you guys. Hope you enjoyed. Bye bye. Thank you for reminding me, Adam. Elections for UFSIT board members are happening in approximately a month. The forms to sign up will come out tomorrow, hopefully. And so, yeah, keep an eye out for that. Have a great day, guys.